Differentiation of exponential and logarithmic functions. Hello everyone. To begin, let's recall that in our previous sections, we spent some time exploring the nature and general properties of exponential and logarithmic functions to build a strong foundation. Now that we understand how these functions behave, we are ready to move forward and apply the principles of calculus to them. In this specific subsection, we will focus on the fundamental rules for differentiating two essential functions: the natural exponential function, e to the power of x, and the natural logarithmic function, log x. These rules will serve as the building blocks for the examples and real-world applications we will discuss in the upcoming slides. The natural exponential function. Now that we have reviewed the nature and properties of these functions, let us dive into the actual calculus. We will begin with the natural exponential function, denoted as f of x equals e to the power x. This is one of the most significant functions in all of mathematics, primarily because it possesses a very unique property regarding its rate of change. Let us look at the derivative rule. The derivative of e to the power x with respect to x is simply the function itself. Mathematically, we express this as d dx of e to the power x equals e to the power x. To understand this geometrically, it means that at any point on the curve y equals e to the power x, the slope of the tangent to the curve is exactly equal to the y-coordinate of that point. To illustrate how to apply this in a problem, let us work through a step-by-step example. Suppose we need to find the derivative of the function y equals 7e to the power x. In step 1, we identify the constant. We can see that the function consists of a constant, 7, multiplied by e to the power x. According to the constant multiple rule of differentiation, we can pull the constant outside of the derivative operation. Therefore, dy by dx equals 7 times the derivative of e to the power x with respect to x. In step 2, we apply the fundamental rule we just discussed. Since we know that the derivative of e to the power x is simply e to the power x, we substitute this into our expression. This gives us dy by dx equals 7 times e to the power x. As a final result, the derivative dy by dx equals 7e to the power x. Once you are comfortable with this exponential rule, we will move on to the next slide to discuss the natural logarithmic function, which is the inverse of the function we have just analyzed. The natural logarithmic function. Now that we have explored the natural exponential function, let us turn our attention to its counterpart, the natural logarithmic function. The natural logarithmic function, denoted as f of x equals log x, where the base is the constant e, is the inverse of the exponential function we just discussed. While the exponential derivative was unique for being the function itself, the derivative of the natural log results in a simple algebraic fraction. Let us look at the derivative rule. The derivative of log x with respect to x is the reciprocal of x. To put this in mathematical terms, d dx of log x equals 1 over x. Before we proceed, please take note of an important restriction. This rule is valid only when x is greater than 0. This is because the logarithmic function is only defined for positive real numbers. You cannot take the log of 0 or a negative number. To help you visualize this, let us work through a step-by-step example. Suppose we need to find the derivative of the function y equals 4 log x. In step 1, we identify the constant. The function consists of the constant 4 multiplied by log x. Just as we did with the exponential example in the previous slide, we can use the constant multiple rule to move the 4 outside the derivative. This gives us dy dx equals 4 times the derivative of log x. In step 2, we apply the fundamental rule we just learned. Since we know that the derivative of log x is 1 over x, we substitute this into our expression. This results in dy dx equals 4 times 1 over x. For our final result, we simply multiply the constant by the fraction, giving us dy dx equals 4 over x. Understanding these two fundamental rules, for both the exponential and logarithmic functions, is essential, as they will allow us to tackle more complex real-world applications, which we will discuss in the next slide. Real-world application, growth and decay. Now that we have established the fundamental rules for differentiating exponential and logarithmic functions, let us examine why these derivatives are so significant in practical, real-world applications. Consider a biological population, such as bacteria, that grows at a rate proportional to its current size. This means that as the population increases, the speed at which it grows also increases. We can model this specific behavior using the exponential function. P of t equals p0 times e to the power of kt. When we differentiate this function with respect to time t, we are calculating the instantaneous growth rate. Recall from our previous discussion on the natural exponential function that the derivative of e to the power of x is simply e to the power of x because of this unique property. The rate of growth in our population model is directly proportional to the population size at that exact moment. This mathematical relationship is precisely why exponential functions are the standard choice for modeling various phenomena, including population growth, compound interest in finance, and radioactive decay in physics. Having seen how these functions operate in practice, it is crucial that we now look at some common mistakes to avoid when applying these differentiation rules, which we will cover in the next slide. Common mistakes to avoid. Now that we have covered the fundamental rules and seen how they apply to real-world growth, let us look at some common pitfalls to ensure you avoid these mistakes in your assignments and exams. First, let us discuss the issue of confusing the bases. A very common error is assuming that the derivative of any exponential function, such as a raised to the power of x, is simply a raised to the power of x. Please remember that this unique property is only true for the natural base e, which we explored in the second slide. For any other base, the derivative of a raised to the power of x is a raised to the power of x multiplied by the natural log of a. Second, be mindful of logarithm-based confusion. In high school mathematics, and specifically within the NCERT curriculum, the notation log x usually refers to the natural logarithm, which has the base e. However, if you encounter a logarithm with a different base, such as log base 10 of x, the derivative is not simply 1 over x. Instead, it is 1 over x times the natural log of 10. I strongly advise you to always verify the base of the logarithm before you begin your calculations. Lastly, do not ignore the domain of the function. As we mentioned when introducing the natural logarithmic function, the rule stating that the derivative of log x is 1 over x is only applicable where x is greater than 0. This is because the logarithmic function is only defined for positive real numbers. Consequently, you cannot differentiate log x at x equals 0 or for any negative values of x. Keeping these precautions in mind will help you apply the rules accurately as we move toward our final key takeaways. Key takeaways. All right, let us wrap up this session by summarizing the key takeaways from today's lesson. First, let's recap the natural exponential function, e to the power of x, as we discussed in the earlier slides. This is a truly unique function because it is the only one, aside from constant multiples, that remains unchanged when differentiated. To put it simply, the derivative of e to the power of x with respect to x is simply e to the power of x. Secondly, remember our discussion on the natural logarithmic function, log x. Its derivative is a straightforward algebraic fraction. Specifically, it is the reciprocal of the variable. In other words, the derivative of log x with respect to x equals 1 over x. Finally, it is important to realize that these two fundamental rules are not just isolated facts. They serve as the essential building blocks for more advanced calculus. Once you have mastered these basics and are mindful of the common pitfalls we mentioned, you will be well prepared to handle more complex differentiation problems involving the chain rule, which we will cover in our next set of lessons.